Hi, today we are going to derive the equation for Vane Shear test. As we know, Vane Shear test is a test to get the strength of soil. And any test will be more interesting when you know the concept of it, when you know how to derive the equation and where the equation came from. So let's start with our Vane Shear test equation. When we look at the field tests for determining the soil strength, we can see that we have several types and several tests to do in the field, and these are the major types. So when we look at the types, we have here the Vane Shear test, we have the standard penetration test, cone penetration test, the borehole shear test, the flat diatometer test, the pressure meter test, the plate load test, and the geophysical methods, which are other types of methods. So here we are going to basically focus on the Vane Shear test. Okay, when we look at the word vane in Google and search it, we'll find that the definition is a broad blade attached to a rotary axis. So the name came from the instrument or the equipment itself. So when we look at the equipment, it shows in this way. So these are the blades. This is the first blade, the second blade, and these are the blades. Okay, and this is the rotary axis in the middle of it. So this rotary axis is going to rotate to move those blades to form a cylindrical shape in the soil. So what will happen if I rotate this piece of vane? I am going to get a cylindrical shape. This is my cylindrical shape. Let's assume it in this way. And in this cylindrical shape, I am going to get, while rotating it, I am going to get shear stress distributed on the surface area of that cylinder, which is an imaginary cylinder. Great. So now when we look at the equation, how can we get our equation? Okay, so when we rotate an object, okay, we are keeping a torque. Okay, so now to derive this equation, okay, for the Vane Shear test, the torque is equal to moment 1 plus moment 2. So what is moment 1? Moment 1 is the moment created by the side forces. When I took out the side forces, I mean those, let me keep in the same color as green. So when I am talking about the side, I'm talking about those four sides. This is my first side in green, the second side, and here's my third side. Okay, so these are basically the four sides. Okay, so when I rotate this vane, by rotating this vane, these four sides are shaping a cylinder in this way. So the first moment is the moment created by the side forces. Okay, the second moment, which is moment 2, is the moment created by the top and bottom forces. The top and the bottom forces are the forces here in the top, which can be in this circle, which takes the whole radius. It can be a part of it. It can be even a smaller part of it. So this whole things This whole thing, sorry, expresses the top and the bottom as well. It has the same idea for both. So when we start with the first moment, moment 1, before starting with the first moment, let me take in general. Okay, as we know, any moment is equal to the force times the perpendicular, let me draw a perpendicular distance. Right? So when we work on moment number 1, it will equal to, here as we know, we are having our CU as the shear stress on the whole surface, and the green color is talking about the side forces. So this shear force is distributed on the surface of the cylinder, and as we know, any stress is the force on the area. So if I am going to get only the force, I'll multiply the stress by my surface area. So here, what is my force? My force is consisted of the product of those two things. First of all, here I have my CU, which is the shear stress. I'll multiply this shear stress by the surface area of the cylinder. What is the surface area of the cylinder? It is the circumference of the circle, okay, which is pi d, which is equal to 2 pi r, times the height. Just assume that this height is equal to h, times height, which is h. And now we are going to the perpendicular distance. What is the perpendicular distance? If this thing is rotating, so my perpendicular distance will be the radius from here till there. For each side of it, for this side I'll have the same radius, for the other side I'll have the same radius, for all the four sides. So this is the radius, or d over 2 we can say, which is diameter divided by 2. So my perpendicular distance is d over 2. When I multiply all the terms together, I can get my moment number 1 in this shape, d squared hc. CU, sorry. So this is my moment number 1. So now when I work on moment 2, moment 2 is the moment created by the top and the bottom forces. So let's keep a line and now work on moment 2. Again, moment 2 has the same idea, but for moment 2, I can keep this force in different radius. Like for example, I can put stress times the total radius. I can put the stress times a part of the radius, or this circle can be in any part. Okay, so in this kind of things, okay, so when we are dealing with the surface, this whole surface with the changing radius, we'll be doing our integral. So because we are having top and bottom, we are going to say that moment 2 is equal to 2 times the integral. What's my integral? It is from 0, radius 0 to radius d over 2. So from 0 to d over 2. And what am I going to calculate for each circle of them? For each circle, what am I going to calculate? So first of all, I'm going to get the same idea for the previous equation. I'm going to get the circumference, which is 2 pi r, okay, times the shear stress, which is Cu, times r, which is the perpendicular distance. So those two will summarize my force, and this one will summarize my perpendicular distance as a moment. When we talk about moment, my force is summarized in those two, and my perpendicular distance is the r. And now, because we have the integration here, we'll keep dr, so we can change the r's from 0 up to d over 2. We can now keep this moment, which is moment 2, and in another order. Let's say we can put 4 pi c, take the constants out, 0 d over 2, and inside I can keep r squared dr, and this one will equal to, let me change the color, 4 pi c r cube over 3 from 0 to d over 2. Let's continue in a new page. So after that, we are going to keep the d over 2 value in it. We are going to get 4 pi c d cube over 3, and we are going to take the 2 down, so here I'm going to have 2 cube, close the bracket. So in general it can be done in this way, pi d cube over 6, by cancelling the 4 with a part of the 2 cube, and this will be my moment 2. My moment 2. Now when I have a look at moment 1 and moment 2, okay, now I'll be starting with going back to the main equation, which is the torque. Okay, so now I'll write here my torque equal to moment 1, which is half pi d squared h